Let us now study the uniform angular acceleration case in a little bit more depth. Okay, so what does that mean, uniform angular acceleration? That means alpha is constant. So this is the case that we are going to spend more time on. So here I have a particle that is moving around like this. This is the initial position. This is the final position. Okay, initial and final are just two time intervals, two time instants. So this is the time instant Ti, this is the time instant Tf. Tf minus Ti, I should be calling it delta T, but I am going to call it T. So the time interval, I'll just call it T. This is the initial angle. It was not necessarily starting at this point, it is starting at some place. So we'll call it theta I, and the final position is theta F. So we will talk about a angular displacement delta theta, which is theta F minus theta I. So I hope this is clear. First, let us just get the basic equations in place. Alpha, what is the definition of alpha? Omega final minus omega initial by the time interval, I'll call it T. Now, alpha bar is what I should have called it, right? Average angular acceleration, but it's uniform, so I'll just call it alpha. So if this is the case, then you can take alpha T, right? So if I took it to that side, I'm going to get alpha into T is omega final minus omega initial. So we can write omega final. If I take it to that side, I'll get alpha T, and I can bring the omega I there. So I'll get omega I plus alpha into T. So this is our first equation, right? It is the same as this equation. Just multiply, you get alpha T plus omega I plus alpha T is equal to omega F. Okay, so this is the first equation that we are going to keep using continuously. It is nothing except the definition. It is the definition of alpha, except that you know that alpha is constant. I should have, instead of using an alpha bar, I am just using alpha because alpha is constant. So this is the first statement. The second, okay, is something that we will derive starting from something even more important. So I will write a statement here. I am going to put a star so that you see that this is the most important statement. The most important statement is when you have uniform angular acceleration, only for uniform angular acceleration, we can write average angular velocity as final velocity plus initial angular velocity. So final angular velocity plus initial angular velocity by 2. Okay. For average angular velocity, you can just write final angular velocity plus initial angular velocity by 2. Only valid for uniform alpha. Is that okay? It's only valid for uniform alpha. Remember that in general, this is always true. What is the definition of average angular velocity? It is delta theta, right? Delta theta angular displacement divided by time. This is always true. But this is not always true. This is only true for uniform alpha. I have not proved this. I am going to assume that this statement is something that is valid. This is the most important statement. Okay? But from this statement, if I combine this and this, I can find something interesting. So let me write it. I can write average angular velocity is omega final. Omega final is omega initial plus alpha T plus omega initial by 2. And if I look at this, I get omega final, omega initial plus omega initial, 2 omega initial by 2, which is omega initial, plus alpha T by 2, so half alpha T. Okay? That's such an important statement that I'm going to write that statement somewhere here. I'll call it the fourth statement, but I'll put a star because you'll see that that is the most important statement to keep in mind. So let me write that down. So I will write delta theta by T. What is this? Always it is equal to average angular velocity. This is always true, right? This statement. But you can also write average angular velocity as omega final plus omega initial by 2. In the special case of this statement, this part of the equality is valid for all cases. This part of the equality is valid only for constant alpha. And then we can rewrite this. If this is valid, then you can always rewrite this as omega initial plus alpha t. So 2 omega initial plus alpha t by 2. So omega initial plus half alpha t. Right? Now this statement, I want you to remember. We will see that there are lots and lots of uses for this. Okay? This is the foundation for all the rest of the equation that we are getting. Because once I've got this, now look at this. Delta theta by t, displacement, angular displacement by time, is equal to omega initial plus half alpha t. So if I took the t to that side, what is going to happen? I can write our second equation. Delta theta is omega initial into time plus half alpha t square. All I've done is to take the t to that side. So omega initial t plus half alpha t square. So this is what is our second equation. And then let's write the third equation. Again, it comes out of this. That's why I write this as a very, very important statement. Okay? The people usually talk about the first three equations, but this fourth one is probably the most important equation. Okay. Let us look at the third one. So the third one, if you see, delta theta by t is omega final plus omega initial by 2. But alpha is omega final minus omega initial by t. If I just multiply these sides together and those sides together, what will I get? I will get alpha into delta theta by t. This is alpha, this is delta theta by t. And on that side, when I multiply omega final minus omega initial, omega final plus omega initial is omega final square minus omega initial square, right? A minus b into a plus b. And then below you have t and 2, so t and 2. You can cancel the t out and you can bring it here. So you get 2 alpha into delta theta. 2 alpha into delta theta, right? 2 times acceleration into displacement is equal to omega final square minus omega initial square. So where did this come from? Just a little bit of algebra using the first equation and using the fourth equation. So actually the second equation comes out of the fourth equation straight away. Just simply multiply, you get it. The third equation also is basically just a product of the first and the fourth. So these three equations, right, this statement, this and this, these three are the usual uniform accelerated motion except in the angular case. So we say equations of uniform angular acceleration. But what I would like you to remember, and this is what I want you to think about because it's not usually emphasized in school, is the most important equation is average angular velocity for the uniform angular acceleration case is final value plus initial value of the angular velocity by 2. You can also write it in this form. When we write it in this form, you can see that this and this look the same. Think about it. Omega initial, alpha times t, this is alpha times t by 2. So you can also think of this as angular velocity instantaneous at half time. I have written this in a weird way, but if this was at t equals 0 and this is at t equals t, this is at t equals t by 2. Because if I substitute t by 2 here, what will I get? Omega initial plus alpha times t by 2. We won't use it right now. Okay, but if you have learnt our straight line motion trick, this basically turns out to be a very useful thing for many problems. Same principle, same idea. Okay, but this I definitely want you to remember because this is extremely important. Average angular velocity is final plus initial angular velocity by 2, and it is always equal to, this part is always true. This is only true for uniform alpha. So this is always true. What does it mean? Displacement, angular displacement by time is equal to this, which means angular displacement can be found once you find average angular velocity. Now, I want you to compare these equations with the equations that we already know. So for example, what does this equation look like? What is this part? This part is A equals V minus U by T. And from that you can find V equals U plus AT. This is the equation that represents final angular velocity is initial angular velocity plus alpha t, right? Except we use U and V. There we write omega final minus omega initial because we have run out of variables. We don't have more variables, so therefore we are doing that. Okay, the second equation, what is this? This is S is ut plus half at square. This is angular displacement, this is linear displacement, omega it plus half alpha t square. Now you may be wondering, why do I have S, why don't I have a symbol there? That is because we have run out of variables, so we are using delta theta. But if I wanted to do the same here, I would have called it delta x, right? Remember what is S? It is delta x. So delta x is the change in position, it's called displacement. This is delta theta, change in angular position, angular displacement. Same, exact same equation, no difference. And then the third one is 2as, right, is v square minus u square. And here you have 2 alpha delta theta. Delta theta is the same as displacement. If I wrote it here carefully, I would have written 2a delta x is v square minus u square. Of course, nobody wants to remember it like this, so you remember it as 2as is v square minus u square. 2 alpha angular displacement, delta theta is omega f square minus omega initial square. So I hope the ideas are all exactly the same. And the last one is exactly the equation that you would know, which is s by t or delta x by t. This is average velocity. But what was the most important idea we learned there? V plus u by 2 is average velocity for uniform acceleration. This is always, and this was only for uniform acceleration, right? Same idea that you use here. And of course, you can simplify this to u plus half at, like we did that here. We won't use that much, so let's not worry about that. So I hope it is clear. These 4 equations we are going to use a lot. So you should definitely remember all of them. Okay. So very simple, straightforward equations. We could have derived this by using a little bit of calculus, which we are not going to do. Right? You can say alpha is constant, right? Start from d omega by dt equals alpha, and then you can do some integration and find it. It just unnecessarily makes things sound more fancy. This gives you the basic idea. I want you to keep these equations in mind, of course, but I want you to also keep in mind that always average angular velocity is delta theta by t. So keep also in mind that you can write delta theta as average omega into time. Keep this in mind. It's the same as this equation. And it's very easy to find average angular velocity. So I hope that is clear. Best thing to do is to apply this in a bunch of questions, because then that will help us understand this a lot better. So let us look at a few examples. Let us now look at this example question. There is a particle that is going around in a circular path. Its initial angular velocity is 4 radians per second at t equals 0. And we want to look at quantities at t equals 4 seconds. We want to calculate what is the angular velocity at t equals 4 seconds, the displacement, all that. It is given that angular acceleration is constant, alpha is 2 radians per second square. That's given in the question. Then the first part, which is to find what is the final angular velocity, all we have to do is to say initial angular velocity plus alpha times time. Initial angular velocity is 4 radians per second, alpha is 2. The time interval from t equals 0 to t equals 4 is 4 seconds. So that is just into 4 here. So 4 plus 4 into 2, so 4 plus 8, 12 radians per second. So that means the final angular velocity here is 12 radians per second. If I now want to find average angular velocity during this time, because it is uniform angular acceleration, average angular velocity is final angular velocity plus initial angular velocity by 2. Remember, only valid for uniform angular acceleration. It is uniform angular acceleration, so no big problem. So this is 12 plus initial is 4 by 2. So this is how much? 16 by 2, 8 radians per second. So the average angular velocity from 4 to 12, something in between, is 8. Okay. Now let us look at what is the angular displacement, delta theta. Initial angular position is that, final is this. This is delta theta. We can directly write delta theta is average angular velocity into time. We already calculated average angular velocity is 8 radians per second. Time interval from here to there is 4 seconds. So if I multiply by 4 seconds, it basically is going to give me 8 into 4, 32 radians. So this is one way to calculate, where I am using average angular velocity. Another way to calculate the same thing is to use the formula delta theta is omega initial into time plus half alpha t square, in which case I didn't need the average angular velocity. I have already calculated it, so I am using it. Otherwise, I would have just used this formula. What is omega initial? 4. Time interval 4 seconds, because it is going to travel for 4 seconds, right? So the t, delta t is 4 seconds. Okay, so omega initial into t plus half alpha is 2 into t square, which is 4 square. And so if I cancel this out, I have 16 plus 16, 32 radians, right? So this gives us delta theta by using the formula. That gives us delta theta by using average angular velocity into time. Both should give you the exact same answer. Very, very simple, straightforward application of the formulas. Okay, let us now look at a slightly different type of example. So in this question, there is a particle that was going around at t equals 0, okay. So at initial time, so t initial is 0 seconds. At that time it has an angular velocity, initial angular velocity of 3 pi radians per second. And let us say that the object has been switched off. Let's think of it like a fan or something that has been switched off, and it is decelerating uniformly. It is given that alpha is constant, but it could be positive or negative. But if it was positive, it won't actually stop. So it is negative, which basically means that the alpha is in this direction. We will think of alpha as being negative, that's all. So we don't have to worry about the direction. So this fellow starts like this. It completes one revolution in 0.8 seconds. You can see that we can now use that information to find alpha. Well, if it makes one full revolution, that is, it comes back where it started, what is the angular displacement for just that part? We are also looking at the total angular displacement. But suppose it just comes back at that part, what is the angular displacement? It is 2 pi. So delta theta for that portion is 2 pi. But angular displacement must be equal to omega initial, right? Omega initial into time plus half alpha t square. So if I use that, I can write 2 pi is 3 pi into 0.8, because I have been told that time is 0.8, plus half into alpha into 0.8 into 0.8, half alpha t square. If I solve this, I will be able to find out what is alpha. Okay, so this is 2.4 pi. So let us cancel this out. This is going to give me 0.4, right? So this is 2.4 because 3 into 0.8. So if I bring it to this side, 2 minus 2.4 is minus 0.4 pi is equal to 0.4 into 0.8. I'll write 0.8 as 4 by 5 into alpha. This 0.4 and this 0.4 can cancel out, and so I get alpha is minus 5 pi by 4 or minus 1.25 pi radians per second square. Hey, I have got a negative alpha. Is that okay? Yes, perfectly okay. You should get a negative alpha. Otherwise, this object would have speeded up. Let us quickly check something. If it ran at same 3 pi throughout, the time it would have taken is, it would have done 2 pi by 3 pi. If it was constant omega, which means it would have taken 0.66 seconds. It has taken more time than 0.66 seconds, which basically means it is slowing down. If it took less time than 0.66, it would have been speeding up. But we know it's taking more time, so that means it must be slowing down, right? So we know that it is slowing down, alpha must be negative, so we have actually found out what the alpha is. Could I have also done this in a different way? So the first part of the question I have answered. It is minus 1.25 pi radians per second square. So that is the alpha. It is constant and we can do that. Could I have done this in a different way? Yes, let us think about that. If at this point when it reached, let me call that omega, okay. So if I write average omega as omega at that point, okay, plus omega initial, which is 3 pi by 2. I can do that, right? Because it is uniform alpha, into the time interval of 0.8. What is this? Average angular velocity into 0.8 must be the angular displacement, which is 2 pi. This must be equal to 2 pi. So that means omega plus 3 pi must be 2 into 2, 4 pi by 0.8. And so if I cancel this out, this is 0.2. And so that is going to give me 5 pi. It tells me that omega is 2 pi. 5 pi minus 3 pi, 2 pi radians per second. So that means when it comes back the second time, its angular velocity will be 2 pi radians per second. After one trip, when it comes back, its angular velocity is 2 pi radians per second. You can see that very quickly now, because it's 3 pi plus 2 pi is how much? 5 pi by 2, 2.5 pi. So the average angular velocity is 2.5 pi into 0.8 is going to be 2 pi. Right? So you can do that calculation quickly. But let us not worry too much about that. So now with this I can find alpha. Alpha is final angular velocity minus initial angular velocity by the time 0.8. So this is minus pi by 0.8, minus pi by 0.8 is 4 by 5. So that basically gives me minus 1.25 pi radians per second square. So there I use the formula directly. Here I use the average angular velocity into time must give me the displacement. I use this to calculate what is alpha, because once I find what is the omega after 0.8 seconds, you know the initial omega, you know the final omega, you can calculate what is the angular acceleration. So I hope this part is clear. Now let us but look at the time to stop. Once I found alpha, these are both answering the same question. Time to stop. Basically, let us say that after it is made one round, it continues and somewhere here it stops. Okay, it goes one round and then comes here and it stops. Okay, so what is the total time that it has traveled for? Final angular velocity here will be 0. Omega final is 0 because it stops. Right? But omega final must be omega initial plus alpha into t. But you already know alpha is minus 1.25 pi. So this is 3 pi minus 1.25 pi into t. This is equal to 0. So therefore t must be 3 pi divided by 1.25 pi. So 3 by 5 by 4, right? This 5 by 4, so it goes up there. So if you see what is this? 12 by 5. So t is 12 by 5, which is 2.4 seconds. So the time it takes to stop is equal to 2.4 seconds from the initial time it started. It took 2.4 seconds to go around. What is the total angular displacement that the object has during this time? Well, this we can use the formula delta theta is omega I into time plus half alpha t square. There's a lot of work to calculate. So I'm not going to use it. If you want, you can substitute here 3 pi into this time 2.4 and calculate. I won't do it. Okay. You will find that you will get the same answer if you use it. What I am going to do is that I will write delta theta is average angular velocity into time. Average angular velocity is initial angular velocity plus final angular velocity by 2 into the time 2.4 seconds. Right? Do I know the initial angular velocity? 3 pi. What is the final angular velocity? 0. So this is 3 pi plus 0 by 2 into 2.4. So if I cancel this out, this is 1.2 into 3. So this is 3.6 pi radians. Okay. So the total angular displacement is 3.6 pi radians. Okay. That is the total amount of displacement. Now if it had gone one full round, it will be 2 pi. If it had gone 2 rounds, it will be 4 pi. This is slightly less than 4 pi. So what do you think the object did? It started here, it went one trip, then it went one more trip and then stopped here, right? Before it reached the second round here. So did it complete 2 revolutions? No. If I divide by this by 2 pi, you see it is about 3.6 divided by 2 is 1.8. So it has made 1.8 revolutions. It did not make 2 revolutions. It was slightly less than 2 revolutions. So it started, went round once, went round the second time, but it stopped before it reached the starting point again, right? So it made slightly less than 2 revolutions. So I hope this is clear. So when you are given information, some information, we can use these equations to solve. You will find that there are multiple ways to solve. Like for example, I found alpha directly by using the formula. But you can also use this powerful tool, which is average angular velocity is final angular velocity plus initial angular velocity by 2. Very, very powerful tool. And average angular velocity into time is delta theta. Okay, these two we can use for uniform angular acceleration in a very powerful way to solve problems. We have now learnt a lot of different equations for uniform angular acceleration, and the real best way to understand it well is to solve a